A carbocation is a molecule in which a carbon atom has a positive charge and 3 bonds. This carbon is sp2 hybridized with a vacant p orbital, making it highly reactive and electron deficient. Carbocation stability depends on the number of alkyl groups attached to the positive carbon. Stability increases from methyl to primary, secondary, and finally tertiary, which is the most stable configuration. Stability is achieved through hyperconjugation. This occurs when the electrons in adjacent carbon-hydrogen sigma bonds overlap with the empty p orbital, partially neutralizing the positive charge. The inductive effect also plays a role. Alkyl groups are electron-donating. They push electron density through sigma bonds toward the positive carbon, spreading the charge over a larger volume. In standard Markovnikov addition, the hydrogen atom adds to the carbon with more hydrogens to form the most stable carbocation intermediate, leading to the major product. Anti-Markovnikov addition occurs when the substituent attaches to the less substituted carbon. In hydroboration, the boron atom prefers the terminal carbon due to less steric crowding and electronic factors. Anti-Markovnikov hydrobromination happens via a radical mechanism. It begins with the homolytic cleavage of peroxides, which generates highly reactive alkoxy radicals. The alkoxy radical abstracts a hydrogen from HBr, creating a bromine radical. This bromine radical is the species that will actually attack the alkene double bond. The bromine radical adds to the terminal carbon because it results in a more stable secondary radical intermediate. This mirrors the stability logic seen in carbocations but results in different connectivity. By looking at the reaction coordinate, we see that the pathway involving the most stable intermediate, whether it's a carbocation or a radical, has a lower activation energy and is therefore favored. To summarize, Markovnikov reactions favor the most substituted carbon via carbocations, while anti-Markovnikov reactions use different intermediates like radicals or boranes to target the terminal carbon. Understanding the stability of intermediates allows us to predict the regiochemistry of organic reactions. Mastery of these mechanisms is key to synthetic chemistry. Generated by Vision Solve AI.